I asked you to try this assembly. This is B. And this is Q. So, can you draw the load displacement curve for this? What will be the difference? The only difference will be that this resultant here, this will be B plus Q. What will be these reactions? This is H by 2, this is also H by 2. Okay, so how much will be this reaction? You can take moment about this one. So then V into H plus Q into H by 2. Okay, that is the clockwise moment. Anti-clockwise moment will be equal to so this will give you R. The rest of the procedure will be same. Right. Okay. So rest of the procedure will be same as we have followed earlier. I will tell you in which case we will require this. So before going to that, let's go to the full building. So far we have analyzed different types of assemblages. Okay, these assemblages will form part of the full building. So let's take a full building. Okay, first I will apply a force at the top only. And this is delta roof, and this shear here will be equal to Q, and the story shear will also be constant because the force is acting at top only. So all the stories in the first story, second story it is also Q, and in the third story also it is Q. So story shears are same. In real building, the force will not be acting at top only. Okay. In that case, you need to know the variation of this force. Okay, and then let us say this is Q1, Q2, Q3. So in real building, the story shear will be like this. Here it will be Q1 plus Q2 plus Q3. Here it will be Q2 plus Q3, and here it will be equal to Q3. In a real building, actually the story shear will go on changing. Okay, and not only that, the forces will act at the mid joint also. So when you are considering the points of contact here, So you can see that this assemblage is similar to what I have given you here. So there is a shear force as well as additional Q, and as a result, in half of the story assemblage, the shear will be different and bottom half it will be different. Okay, so let us do first the simpler case where the story shears are uniform. Then we will go to this non-uniform case. It is subjected to only a force Q at the top, and we know the behavior of different sub-assemblies which we have obtained by assuming point of contraflexion and separating our columns and beams at those points of contraflexion where the moment is given. Okay, so I told you that these three assemblages here, these are in parallel. Okay, so what we will do, we will define the stories like this. So this one I am defining as a story 1, this second one as 2, and this one as 3, and this as 4. So rather than defining the story from floor to floor, which is our conventional way, we are defining stories here between the mid height of the column where point of contraflexion is to the mid height of the upper story where the point of contraflexion is, because our assemblages are of this height. Okay. Now, taking any one story, this new story here, or set of sub-assemblages, I can combine them. Okay. You can see that this whole assemblage will move together because it is connected by rigid flow. So this is going to move together. That means the displacement is going to be the same. And when the displacement is same, we can add them in parallel. Okay, you know how to add linear elastic springs in parallel. Here we don't have linear elastic springs. We have Q versus delta. So let me call this assemblage as 2-1, this assemblage as 2-2, and this assemblage as 2-3. Second story, third assemblage. Okay, so for 2-1, you have already plotted Q versus delta. How much was this value? Can you look into your notes and tell me? MB by H. And this displacement? Sorry. Let me create this. Okay. So this was MB by H square by 6 E L by ID H by that will be H, not H square. Not H. Okay. Now second assemblage 2-2. This is for 2-1. Let's plot for 2-2. Again, this was similar, but this value was different. How much was that? MB by H?
Yes. 2 MB.
Okay. And the displacement?
MB by H over 6. L over IP. Plus H over IC.
Okay. And for 2, 3, it will be same as 2, 1. You agree? Agree? You can get numerical values, then rather than these expressions, you will have numerical values. These 3 are in parallel. Okay. So how we can add them? I can combine those and get a Q, let me call it Q2 versus delta. Or I can also call it as V2, the shear versus delta. The shear in second story, okay, versus the displacement in the second story. How will I get that? I have to combine these in parallel. Combining in parallel means at any given displacement, you check the forces. Okay, so for any given displacement, check the forces and forces you add. Okay, so for example here, let me call this as delta 1, this as delta 2, and this will be delta 1. Okay, just to replace this expression. So at which displacement? If you see, initially all are parallel. Sorry, all are linear. So when those are linear, you can just add them till the first sub-assemblage yields. So which is the first sub-assemblage to yield? Here. You are increasing the displacement and then there will be first yielding of sub-assemblage. Where that is applied? 2, 1. Okay, so this is going to yield first. So at delta 1, so up to delta 1, this will be constant. Sorry, the slope will be constant.
Sir.
It will be increasing by, yes.
How you decide first one will be the
Whichever is yielding at the lower displacement. So which one is larger, delta 1 or delta 2?
delta 1?
Delta 1 is larger.
Delta 2.
Delta 2 is larger.
Yes.
So whichever is lower, that is going to yield first. So delta 1 will be reached first before delta 2. And at delta 1, this will yield and this will yield. And here you will calculate the force corresponding to delta 1. So this will have this much force, this will have this much force, this will have this much force. Until this point, all the three have linear relationship. Okay, it will be more clear. Let us take a numerical example. Then you will be able to understand it better. So let me do this for 2-1. Let us say this is 1000 kilometer and this displacement is 2 m. And let us say this is 10 m. Okay. For 2-2, this is 2000 kilometer cube. The displacement here is, let us say, not 2 mm, 3 m, and here it is 15 mm. And then in 2-3, this will be same as 2-1. Suppose it is like this. I have to add them in V2 versus delta. How we are going to add? You can see at 2 mm till 2 mm. This is also elastic, this is also elastic, this is also elastic. Linear. So you calculate how much will be this force at 2 mm. Can you calculate the linear source? Can you calculate how much force in subassemblage 2-2 will develop at a displacement of 2 m? Because it is linear, you can simply calculate using similar triangle in proportion. 2000 by 3 into 2? 4000 by 3 or 1600 133. Okay, so up to 2 mm it will be like this, and this will be 1000 plus 1000 plus 1333. Agree? Do you agree? At 2 mm, this will apply a force of 1000 mm, 1000 km. This will apply a force of 1000 km. This will apply a force of 1333 km. How much is the total force applied by this story at this displacement? It will be simply sum of the 3, that is 3333 km. What will happen after that? After that, this is not going to take any additional force, this is not going to take any additional force, but this will still continue. Okay, so next event will happen at this point, at 3 mm. So let's say at 3 mm, how much will be the force? 2000. You calculate here at 3 mm, how much is the force? Here at 3 mm, here at 3 mm, and add them. So how much is the force? Yes? 4000. It will be 4000. You can see that here the stiffness is much larger, here the stiffness has reduced. You can calculate the stiffness also. And if you calculate the stiffness, it will come out to be the sum of these three stiffnesses. You can do that because the displacement is same, forces we have added. So the stiffness will be directly added. So this stiffness will come out to be sum of all the three stiffnesses.
Sir,
Yes.
at 3 mm, this 2-1 and 2-2.
Right.
Taking load 0.
Not 0. It is not 0. You can see it is 1000.
Okay. Previously applied.
Yes. So at 2 mm, this will resist 1000 kilonewton. Sorry, at 3 mm, this will resist 1000 kilonewton. This will also resist 1000 kilonewton. And this will resist 2000 kilonewton.
So what is saying about stiffness?
Sorry?
What we were saying about stiffness?
Stiffness. So let us say this stiffness is K1, this stiffness is K2, and this stiffness is K3, which is actually equal to K1, same as K1. So this stiffness K here, you can calculate, this will be equal to K1 plus K2 plus K3. And that's what you have learned in case of your linear elastic springs. If you connect them in parallel, stiffness is simply added. Okay? So you can check that whether this stiffness is matching or not. But once these yield, then the stiffness will change. And this stiffness, you will see, the stiffness contributed by 1 and 3 is 0. So this will be equal to K. What will happen after that? If you take any displacement here, 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 you can see that the force contributed by all the sub-assemblies is same. So it will become flat after that. Till when it will continue? Up to 10 mm. What will happen after 10 mm? The sub-assemblage
2-1 and 2-3 will be.
1 and 3 will collapse. Okay. So when these two sub-assemblies are collapsing, the story will collapse.
The beam will collapse.
Yes. So as we discussed yesterday, you can treat when your beam is collapsing, you are assuming that the story has collapsed or the building has collapsed. That is one way of looking at it. Another possibility is that you say that collapse of the beam is not collapse of the structure. I can still assume that my building is standing. In that case, you can reduce the force here and this can continue up to 15. How much will be this force? 2000. So this becomes the story shear versus inter-story drift diagram. Okay, so V2 is the story shear and delta 2 is inter-story drift. Okay, it is not displacement, it is inter-story drift. What is the difference between displacement of a story and inter-story drift? The displacement is absolute. Okay, inter-story drift is difference between the displacement of the upper story to the lower story. So this is the additional deformation made by this story. Okay. Now,
Sir,
yes.
explain what after 10 mm what is happened.
After 10 mm, this will not take any load.
Yes.
Its capacity will be 0. This capacity will also be 0, but it can still continue
Yes.
up to 15 mm. So contribution of this will be 0, contribution of this will be 0, contribution of this will be 2000. So that's why the total capacity to resist will be 2000. Yes.
If one shows it only for the first phase, let's say B or column, then then you might see that B is small is particular load, but due to that our building is column building. So how to do that?
Yeah, that's what I was saying. So failure of beam and failure of column will have different. If the column has failed, the building has failed. Okay, because once the column fails, the gravity load carrying capacity will be lost. How do we define that our building has failed? Failed is a different term. Failed means that it has stopped serving the purpose for which it was designed. Okay. But here we are talking about collapse, not actually failure, but collapse. So when the collapse of the building will happen? If the column fails, column collapses, then it loses its vertical load carrying. If beam fails, beam collapses, what will happen? It will also lose vertical load carrying capacity, low, in that extent. You may consider that as failure because when you are designing a new building, you will not accept that, or you are trying to determine or evaluating an existing building when it is going to collapse. Okay. In that case, you may accept that one beam failure is not, or one beam collapse is not collapse of the building. Okay. But in case of column, as soon as the first column fails, collapses, building is going to collapse. Okay. Although that is also not always true. If one column collapses, the load gets redistributed. So that load will be taken by the other columns, provided your beams are adequate to transfer that gravity load. So this phenomena is particularly used in case of blast resistant design. So in case of blast resistant design, usually all the columns do not collapse. A few columns may collapse, other columns are intact. In case of earthquake, it is different story. In case of earthquake, generally all the columns will collapse or will reach the same damage state together. Okay. But in case of blast, the situation is different, where some of the columns may be blown away, other columns may be intact. So even if one column fails here, let us say in our building, so this column, let's say 4, what will happen? This portion of the building, okay, this will act like a cantilever, and the beam forces are going to change. So if the building fails just by failure of one column, it is said that the building design is not robust. Okay, so we define this as robustness of design. So robustness of design means that the sequential failure should be avoided. It should not happen a chain type of failure, that one column fails and then whole building collapses. So one column or one beam fails, the building should be capable of resisting the gravity load in the new mechanism. Okay, the new structure will form. So that structure, so we have to check the reinforcement and top and bottom in such a way that when the action of the beam changes, okay, so it is still not part of the codes, but in future, because bomb blasts now are being considered as a routine design, okay, it can happen in any field. So far, we generally in our code we have seen we do not consider the blast problem. We assume that it is a very rare thing which is happening, we are not designing for it. But slowly that perception is changing. Every building may be under threat, especially when you are designing a tall building. If this is a small building, then the casualties will be less. But suppose it is a multi-story building, like that World Trade Center, the number of casualties may be very large. So there, this aspect is also taken into account that the design should be robust. What is meant by robustness of the design? That some of the members I remove. Still, the building should be able to withstand the gravity. Okay. So, in case of earthquake, still this robustness we are not checking. The reason is that in case of earthquake, the damage is distributed. All the columns, theoretically, we should design our building in such a way that all the columns should yield simultaneously. And when all the columns are yielding simultaneously, those are collapsing simultaneously. That is the best way to register earthquake. Okay. If one column is collapsing, other columns which are also almost at the same state, those will not be able to take rest of the force. So that's why in case of earthquake, as soon as the one column collapses, we assume that the collapse of the building takes place. But same is not true for beam, because columns are still intact and columns can resist gravity. Okay, so this definition of collapse, beyond this is debatable. Okay, you can consider the collapse here or you can consider the collapse there, depending on which member is failing, whether the beam is failing or the column. Okay?
Sure.
Yes.
While calculation of this Q1, Q2, we have a course on story and divided into columns as per the ratios of this their stiffness, and we are using complete division delta equal to all columns delta should be equal. So we are not getting delta same for
Sorry?
Here I am not getting delta same for this assembly and this assembly, because these assemblies are moving in direction.
Right.
So
Those are moving together?
those are moving together. So whatever the delta it has, that delta should be it.
Right.
Then why are not getting here?
We are getting the same now.
No.
Why you say that the delta is not same? We are, when this is reaching 2 mm, we have considered here also 2 mm, we have considered here also 2 mm. So all the three have 2 mm simultaneously. Okay? All the three have 3 mm simultaneously. All the three have 10 mm simultaneously. So we have considered that all these are having same displacement. That's why we are able to add them in parallel. If these displacements were not same, we were not able to add them in parallel. Okay. So their applied displacement is same. Perhaps you are getting confused with the capacity. Capacity may be different.
Yes, that will be the stiffness.
So capacity will depend upon the stiffness. So here we are having only one beam. Here we are having beams on both the sides. So their capacities are different. Okay. But the displacement which will be caused by lateral load, that will be same. And we have taken advantage of that in summing up by getting the stiffness or story shear versus interstory drift plot of the story. Okay. Like that we can do for all the stories. So these stories 1, 2, 3, 4 which I have identified, you can do that. And please keep in mind, as I have told in the beginning, the stories I have identified slightly different. Not a conventional way of a story which is floor to floor. Here we have identified a story from point of contraction to point of contraction. Mid height of the story to mid height of the story. Okay. Now, if you see these, suppose this type of curves I can go get for story 1, story 2, story 3, story 4. Can I sum up for the whole building? What you see here, the story shear is same. Displacements are different. Story shear in all the stories is same. Okay, but displacements, interstory drift may be different. Okay, so how we will combine them when the force is same?
Series connection.
Series connection. So let me just assume for story 1, let us say, the load displacement curve is something like this, or V1 versus delta 2000 kilometers, and this I am taking, let us say 5. Why 1? Because ground story you have seen, it is just cantilever column. So these are just cantilever columns, all columns are identical. Let us say all of them are yielding simultaneously. So I will get like this. For the second story, just now we have done something like this. 2 mm, 3 mm, 10 mm, let us say 50 mm. Okay, so no, power of this, no? 2000, no, sorry, this was 3, no, 3, and this is 2000, this one. Okay, story 3 will be same, story 4 just hypothetically I am assuming something. Okay, so let us say this is 1 mm. Just for the purpose of exercise, let us say this is 3 mm. This is 1000 kilometers, 2000. Let us say this.
So even is also hypothetical.
Huh?
One first case is also hypothetical.
All are hypothetical. We have not done any analysis. You will do the analysis as we have done. For the sake of exercise, we are doing. Okay. So this is also hypothetical. 5 mm and let us say 15 mm. Suppose this is the situation.
On y-axis is story shear.
Y-axis is story shear. V1, V2, V4. So this is story shear in kilonewton. Story shear in kilonewton. And here it is into story shear.
The story shearing at first floor is less than 10 seconds.
Maybe. It will depend upon the how much reinforcement you have provided. These are hypothetical.
This is the applied force.
No. This is the capacity. All these are capacities. We have not yet applied, determined what load will come, what earthquake is, what response spectrum is. We have not considered. We have considered what reinforcement we have provided. Okay. What size is there? Based on that, we have calculated MVY, MCY, and then we have plotted these curves. So everything we are doing here is capacity. No demand here. So now what will happen if you consider this? We are adding these in series now. Earlier we have added them in parallel, in series. So what will happen in series? At any given shear, the displacement will be added. Earlier, at any given displacement, we have added story shear. Okay? The forces. Now here, at any given shear, we have to add the displacements.
Sir, the delta is story grip now.
Sorry?
Delta shown in graph is the story grip.
Yes, it is story. So delta root will be sum of all the story roots at any given force. So which is the first force where or till when all the curves are linear, that is 1000. So at 1000 kilonewton, I have to calculate the displacement. Displacement will be addition of this, plus this, plus this, plus this. Addition of all the four stories. Okay? You can see from here. So when you are applying this force, same shear force in all the stories, this will also deform, then this will deform, then this will deform, then this will deform. All four deformations, when you add, okay, you will get this. So at 1000 kilonewton, how much will be the roof displacement? Can you sum up at 1000 kilonewton? At 1000 kilonewton, this is 1 mm. At 1000 kilonewton, how much will be this? 2.5. At 1000 kilonewton, how much will be this? At 3330 it is 2. So at 1000 kilonewton, how much will be this? 2 divided by. So 2 divided by 3.3. How much is that? 0.6. Yes. Sorry. So it will be 2 divided by 3.3. हाँ 1000 के लिए निकाल रहे हैं तो 3033 पर 2 है ना, तो 1000 पर कितना हुआ? 2 divided by 3 into 1000. यही हुआ ना, so that will be 0.6. So this displacement will be how much? 2.5, okay, plus 1, 3.5, plus 0.6, plus 0.6, 4.7. So somewhere here, this will be 4.7. Till this will be D. Okay, so this has inlet. Now after that what will happen? Where the next event is going to happen? At 2000. Let me change this to make it interesting. So let me put it 3000. Same answer.
2500.
2000 से मैं ज़्यादा रखना चाहता हूँ. 2500. So next event is going to happen here. Okay, at 2000. The displacement will be more than 4.7. I mean additional 4.7. So it is going to be more than, slightly more than 9.4. So at 2000, how much is the displacement here? It is still linear. So at 1000.6, so at 2000 it will be 1.2. So how much is going to be this displacement then? Here it is 5, then 1.2 plus 1.2. 7.4 plus at 2000. How much is this? How will you obtain that? You have to obtain from this line. So it will be 1 plus 2500 minus 1000. No. 1 plus 2 upon 1500 into 1000. So how much is that? 2.6. So how much is this displacement? 5 plus 1.2 plus 1.2, 7.4 plus 2.3, 9.7. So where will the next event happen now? Not yet. I mean, at what load? 1000. 1000 is coming down. This is showing the first meter. Yes. So what will happen after that? Suppose I consider the load as 2500. What will happen at 2500? First story cannot take 2500. So the ground story or the first story cannot take load more than 2000. So what will happen? Upper stories can still take. But if the ground story is not able to take load, can the upper stories take? In series it is not possible. In parallel it was possible. That even if one assemblage has yielded, the other assemblages have not yet yielded, it will still take more load. But in series, as soon as one spring is not able to take any load, more load, the other springs will also not be able to take more load because the forces in all the springs have to be equal. So what will happen? After that, it will deform. Okay, now tell me up to what distance? Hmm? 15 mm. 15? 15 mm. 15 mm is of one only. So at that force, Isn't there any displacement of other stories? So how much will be this displacement at which the failure will occur? Failure will occur in the ground story columns. But where? I mean, at what displacement? Hmm? 18? How did you get that?
15 and the fourth displacement of about 2000 and 19.
So what will happen? After this point, the force is not increasing. So you can see that if the force is not increasing, here and here, the displacement is not increasing. Because the curve here is still not become flat. But here, even if the force is not increasing, the displacement will go on increasing. How much displacement can increase? This much. 15 minus 5, delta P, 10. So beyond this, the displacement will occur only in story 1. All other stories, no additional displacement can occur. Okay, because those require increased force for increased displacement. Okay, only this story which has yielded, there the displacement will increase. So you add 10 to 9.7, it is 19.7.
Means above storage will go like this.
Yes,
It will go.
those stories, whatever deformation has occurred so far, same deformation will continue. Those will only move over story 1.
Sir,
Yes.
can you explain again after 2000?
2000. So you take the 2000 load, at 2000 load you calculate the displacement here. At 2000 you calculate the displacement here, which we have calculated as 1.2. At 2000 you calculate the displacement here, we have calculated the 2.3. Is it okay? Then we will add these displacements. So here we obtained at 2005 mm, here 1.2, then story 3 also 1.2, so it becomes 7.4, okay, plus whatever we are having at 2000 here, 2.3. So 7.4 plus 2.3, that becomes 9.7. Okay, so at 2000 kilometer we are getting 9.7.
After 2000.
After 2000, it can't take the ground story to think it like this. This force is 2000. So the force here, this will also be 2000. The force here, this also be 2000 kilometer. The force here, this will also be 2000 kilometer. Okay, but this ground story, the behavior is like this. At 2000, more than 2000 it cannot take. So if you want to increase this 2000 to, let us say, 2001, what will happen? This cannot take any load. Hinges are formed here. This will go on deforming. So it can't take even 2001. At 2000 itself, this will continue till these columns fail. That failure displacement we have obtained from here. So only this is going to move. All other stories will not have any additional deformation. Only story 1 will deform 1. Okay, because this story, after yielding, it can go on deforming without any increase in the force.
So,
Yes.
So then, why we want our desired yield mechanism to form hinges at the base of the column?
desired failure mechanism we want.
And so plaster hinges to form at the base of the column, but when the hinges will form at the base of the column, my structure will.
Yeah, but we want that at the base of the column it should form when the beams in upper stories have yielded.
Okay, first they should have it.
First those should yield, then it should form here. Okay, so that's what we want. So it's not that we want the hinges to form at the base of the column in the beginning. Okay, we want the hinges to form at the base of the column once all the beams in the upper stories have yielded. Here I have taken just hypothetical. This is not a real building. I have just taken some hypothetical case just to demonstrate you how to add the story shear versus interstory drift diagram in a building. Okay, so it's not a real building. The upper stories are going to yield before the ground story columns.
So we will design in that manner that first plaster hinges should form there.
Beams in the upper stories, and then at the base of the column. Okay. So again, this was not a real building case. What is the difference? I have applied only a load Q at the top. In real building, the lateral forces will be applied at all the floor levels. So the story shear here will be like this. So this is Q1, this is Q2, this is Q3. So here it will be so earlier the story shear when we have considered let us say we have considered 1000, then we have considered 1000 in all the stories. Okay, but here it is not same. It is different. Let us say I am assuming a linear variation along the height. So let me say this as Q, this as 2Q, this as 3Q. Okay, so this will become 3Q. This will become 5Q and this will become 6Q. Okay, and you can see that the story shear is changing from floor, but our stories which we assumed, those were assumed from point of flexion to point of flexion. Okay, so I will make another assumption that here and here it will be 6. Here it will be 5 and here it will be 3. Let's do that. Okay. So in the top story it is 3Q. Actually 5Q will start from here to here. I am assuming that 5Q will remain here. Okay. And then here I am assuming 6Q will start from here. So I will get displacement slightly larger. Okay. You can see because in the top portion of this story here it is only 5Q actually, but I am assuming it as 6Q. So the displacement which I will get will be slightly larger with this assumption, but this can simplify. We can still continue with the same story shear drift cases which we have considered earlier. Okay. If I want to consider the actual stress, I can do that also. But in that case, you have to consider this. So for example, in the second story, what I am going to get? The V will be equal to 5Q and then another Q. So you can do that also. So you can do exact analysis also. Okay, but that will be more complex. You have to develop these curves. So we are doing a simplification, and in this simplification, what we are assuming? We are assuming that the story shear changes from mid height of the column. This assumption we are making. Okay, to simplify our calculation. So if this is the case, now can you sum up taking the story shear interstory drift diagram same as we have considered in the previous case. So let me define what is 1 and 2. So this is 1, then this will be 2. This is 1, this is 2 in between, then this is 3, and this is our 4. Okay, can you sum up now? Can we plot dV versus delta root now? Earlier the story shear was same. Now we have to see that the story shears are not same, but there is a relationship between them. What is the relationship? When this is 6 cube, this is 5 cube, this is 3 cube. Okay, so this relationship between the story shears we have to follow. The forces are increasing linearly. So if I have to add this, now the first event happened at 1000 kilonewton, when in story 4 it was 1000 kilonewton. So when in story 4 it is 1000 kilonewton, how much is the shear in the other stories? So story 4 it is 1000 kilonewton. How much it is in the other stories? You can calculate in the same proportion. Yes.
For simplification, we are considering this story shear in between these sides.
Right.
Instead of 3Q, you are taking 5Q for this.
Right.
But these forces, these whatever Q3, Q2 are coming from the capacities of these capacity, whatever the capacity that I can't increase.
No, the Q is not here. Okay, that Q is okay. Do not get confused between this Q and the Q we have used there. All these are variable. So these are not same. That is a common confusion people have. So we have plotted earlier this. All these are variable. Okay, so these can have any value. So it's not that this Q, then how it can become 6Q.
No, I'm not talking that. This is the whatever we are getting this capacity.
Yes.
And capacity we can't consider it as on larger side. Means if
That's
the
what I am saying. Capacity we are considering same, but our capacity is in terms of MVY, not in terms of Q.
Yes, but
Q is just variable. Value of Q will depend on MVY. So
Yeah.
if I am considering, let us say somewhere 4Q in place of Q, that doesn't mean I have increased the capacity. I am just saying that I have to consider the force in proportion to 4Q.
no sir.
Okay, just wait. Because this is a common confusion, you will come to know that when you try it. Okay, so let us try this. So when the force in the top story is 1000 kilonewton, how much will be the forces in the bottom story? That will be right. So when this is 1000 kilonewton, how much will be this? Thousand by 3 into 5. So how much? So 1000 into 5 by 3, sorry. 1000 by 3 into 5. How much is that? 5000 by 3. So, 1. Okay. How much will be this? 2000. So earlier, when we have looked the displacements here and here, okay, we have looked at the same shear. Now we will not look at the same shear. Here, when we are looking for 1000, here in 1, we will look for 2000. Here, in story 2, we will look for 2000, but in story 3, we will look for 1667. Those we will add. Okay, and those we will plot corresponding to a base shear of how much? When this is 1000, how much is the base shear? 2000. So the base shear we will show 2000. Displacements we will add corresponding to that base shear which is occurring in different stories. Okay, so please try this when we meet tomorrow at 4. No, tomorrow there is senior meeting. Tomorrow I will not be able to come. Target will continue with the time. Then we are meeting on Thursday. Thursday. So we will continue from here. In the meantime, try this. Okay. So Vijay, when you will do that, your confusion will be clear. We are not increasing the capacity. Okay. Capacity will remain same. Only thing is that we should be reading the curve corresponding to higher value of fluid.
Sir, what about the base columns?
Base column is 4. So like you have seen here. In the base column, okay, from here to here, it will be 6.
Base
6, you know, from here to here, it is 6.
for 1.
This is 6. Okay. So like that you can. If you consider the actual case where you are considering V and Q, you can get the more accurate answer. Okay, but the computation will become more complex. Idea is, in practice we will never be doing it like this. I will tell you how we will be doing in practice. In practice we will be making a computer model, okay, and we will be doing it. The way the computer model works is different, not like this. It works different. So in practice we will never be doing this. This is only for the purpose of understanding. So in first semester you learned how to visualize the behavior of a linear elastic structure during earthquake. Here we are trying to visualize the behavior of a non-linear, inelastic structure during earthquake. So it is for the purpose of visualization, that how the load is being distributed, how the deformations are getting added up, where the yielding will occur first. Okay, so those things, that information you can get from here. So it is for the purpose of visualization and understanding. Real you will do in, like Tajul will be teaching you, it is a black box, you will get a curve, you will not understand what has happened inside.